So we have 5 years of sales history from 10 stores selling 50 products. Our goal is to predict the future daily sales of each product. This original data came from the Kaggle Demand Forecasting Challenge, and the original goal was to predict sales over the following 3 months. But we are going to blow that goal out of the water by predicting daily sales over the next 2 years. Deep learning neural networks are designed to identify patterns in data, but neural networks will perform terribly when the data is not tagged with the right seasonality triggers. That is why most sales forecasting is done with traditional time series analysis. But done right, neural networks have advantages over the old time series analysis. All time series sales must be split into either a daily, monthly, or annual trend. Neural networks make no such rigid distinction. Furthermore, while a time series analysis must be manually pieced together, a neural network automatically returns a single model. There are 3 types of seasonality we are going to account for: day of the week, monthly season, and long-term growth. Weekday sales are different from weekend sales, so we can one-hot encode the historic sales data with a day of the week tag. And to help the neural network identify the long-term growth rate, we can tag sales with the time since the beginning of the historic data. But we cannot use these trivial methods to tag monthly seasonality. We cannot one-hot encode each month, as we lose the fact that March and April are adjacent. And we cannot use the numbers 1 through 12 to identify months, as we lose the continuity between December and January. Periodic encoding solves these problems by informing the neural network not only the month, but which other months are nearby and how nearby. Periodic encoding works by applying some energy to each of the 12-month input nodes, depending upon the distance the training day is from the month. For example, if the historic sales data is from June 15, then the June energy would be highly concentrated and the June node would be completely turned on. The adjacent May and July nodes would also receive some energy, but the more distant months would get much less. Alternatively, if the sales data is from September 1st, then the energy would be more distributed. Having just started, the September node would not yet be completely turned on, and as August just finished, it would receive almost as much energy as September. Finally, to provide continuity, sales data from December would spill over into the January node. We trained a variety of neural networks to predict future sales using feed-forward networks, recurrent neural networks with long short-term memory, LSTM, concatenated networks, and convolutional networks. We varied the size of the training data between the past 7 days and the past 30 days, and we varied the number of hidden layers and the training time used by different epochs. In all, we trained 7 neural networks and selected the best one to predict future sales. The neural networks were originally trained in Python, and then the models were ported to the KNIME data analytics platform. Python has some distinct advantages. Models can be rapidly prototyped, and it is easy to train models across cloud clusters. But KNIME's visual pipeline also has some advantages. Complex models can be painlessly debugged, and it is easy to explain the model to colleagues. An example neural network that we created was this concatenated LSTM model. In the top branch, we parsed the last 30 days of historic data. The long short-term memory layer remembered previous time series inputs, so it could more easily identify trends in the data. In the bottom branch, we parsed the feature enhancements to the sales, including the day of the week, the periodic encoded month, and the days since start. The modular Keras library made it easy to construct a model and tune it. The models performed as shown in the table and chart. The best model was based upon the research paper LSTM Fully Convolutional Networks for Time Series Classification. This model was then selected to predict the daily sales over the next 2 years. The day of the week sales trend shows 2 things. First, that the neural network is correctly predicting long-term annual growth. The historic sales data from 2013 to 2017 is represented by the bottom 5 curves in the chart. The predicted sales for 2018 and 2019 are represented by the top two curves. The upward shift indicates that there has been annual sales growth. Regressions of both the historic and predicted data agree that total sales are growing at about 5 units per day. Second, that the day of the week sales are consistent. Monday sales are typically the lowest, with sales growing each day through to a peak on Sunday. Historic sales and predicted sales agree on the shape of this curve. The annual sales trend shows the seasonality of sales throughout the year. Again, the shape of the bottom 5 historic sales curves generally agree with the shape of the top 2 predicted sales curves. However, the predicted sales curves are smooth, while the historic sales curve exhibit more of a step function shape. Upon closer inspection, the sales plateaus in the historic data seem to occur during the last week of every month. This may be due to stores regularly running out of stock. The historic sales data was not tagged to catch this trend. If a week of the month tag was used, then it is likely that this step function shape would have also been detected by the neural network. This concludes our analysis. For more details about the model, please follow the link.